All right, so if we look at CS, all right, everybody's okay with one dot on this side. How many dots on O? Everybody's okay with how we start. Yeah. Now, on the other side, you're showing me where the dots go. So CS is going to do what with its dot? It's going to give it to O. So we all know CS is going to lose its dot, and O is going to gain its dot. So CS is going to have a +1. O is now going to have 7 dots. Now, is that the way it's going to stay? No. Because that's what it's done so far. It's gained 1 electron. Is it happy with a -1 and 7 dots? No. So you can't leave it that way. Wait, but I don't get what's -1. It's not going to stay -1. Okay? You've only given it 1 electron. Is O going to be happy with 7 dots and a -1 because it gained 1 electron? No. Okay? So that's not correct. You asked me yesterday how you know that we make up other elements to put on it. That's how you know. O is A, not going to have a -1 charge. And B, it has 7 electrons. It has to have how many? It has to have 8. O has to have an octet. It cannot have less than an octet. So you know you have to, in Caroline's infamous words of yesterday, make up some element to add because O has to have how many electrons? 8. It's non-negotiable. It gets 8 electrons. The question is, what element are you making up to stick over there? Your only options are CS and O. Now, if you add an O over here, O is going to do what? Want 2 more electrons. Is that going to help us if it needs 2 electrons? No. You have to add somebody who's going to donate electrons to that O to give it 8. What is the only element that will donate electrons to the O? CS. That's why we add CS here. Because CS is going to do what with its electron? Give it away. So we're going to add a CS that's going to say, I'm giving my electron away. It's giving it to O. And now O has gained how many electrons? 2. So it has its 8, but it's gained 2 extras. So now it has a -2 charge because it's gained 2. Can you just look at the oxidation? To know how many it's going to gain? No, to find out which number to put up. Sure.
And does it matter what order it's in?
No.
Like, can we have the CS back to back?
Sure. Now, yesterday, the picture you sent me of your homework, you had written CS plus O over here. We don't write CS plus O. The way we do that is on this side, we balance. So how many CS's do we need over here to balance over there?
2.
We put a 2 there to balance the CS's. I already said no. Oh, I'm sorry. It's on the test, not the quiz. Now, AL plus F. How many electrons does AL have? Has 3. So put 3 dots. F has, so put 7 dots. Now, AL is going to do what? Give them all away. So you got AL, and it has a +3 charge. Now, F took how many of those? Took only 1. So I have 8 electrons on the fluorine. And 2 homeless electrons. Those electrons have to have homes. So you got to add something to give them homes. So what are we going to add that can take an electron? An F. F is the only thing that can take an electron. So F has how many electrons on it? Well, it has 7 to start with, right? So if it has 7 to start with, how many can it take? It can only take 1 of these homeless electrons. So now I have how many homeless electrons left? So am I done? No. I got to add another what? Another F. And it has how many on it?
7.
It has 7 on it. And so that homeless electron is now going to slide right in there. And it's got now 8 and a -1. Is it balanced? No, I have 3 F's on this side. So I'm going to put 3 F's on that side.
So the element that loses its electrons, you have to get rid of all of the.
Yes. The one that loses gets rid of all of them. Otherwise, it won't have 8. It won't have an octet. It can't just lose one. It's got to lose them all.
But we leave those blank,
But we leave those what blank?
like the CS and the AL.
Yes, you leave those blank. The ones that lose, we do not draw any dots on. Questions? All right, can I see homework very quickly? What happened in the middle section? You got lazy. Give me a second. That's. Like that. Good. Got something at the top. That whole row is. You got it. You been going out.
Let me see.
Making me hunt for it. Do it. Let me think about it for a second. You have so much no points. You're welcome. If it's possible you do negative points for that, I think we negative. Just for making me stand there and wait on you to find it. Wasting my time. Yeah. What you got? Huh? Oh, I got it.
Yeah, go ahead and.
Kind of pitiful there.
Another 25.
Works for me, it's better than 0.
That's good. Sounds positive.
Sliding all the paper on. So one time I fell asleep on my lap. I was writing paper. I fell asleep on my lap. I woke up. I had like 3 pages worth of F's. Like F. Cause I had fell asleep on the laptop. I was high school.
Back front. Good.
So it's just looking.
Back side. Good.
It's just bliss.
No.
Almost like half of it.
All right. Some of the answers I'm going to call out, some will be on the board. So,
Yeah, we got a book out with attachment.
All right, question 1. Electron shared would be what type of bond? That would be a covalent bond, right? Transferred would be ionic. Triple bond would be covalent. Molecules is positive and negative ions is ions. Ionic. That's where the name ionic comes from. It's the beginning of ionic. All right, metal and non-metal. Ionic, non-metal and non-metal. Covalent within a polyatomic ion. Covalent, they're all covalent. All right, trigonal planar shape. Covalent. Trigonal is another way to say triangular. Some books will say trigonal instead of triangular. It means the same thing. And resonance. It's covalent. It all happens in Lewis structures.
What was 2, 3, and 4 again?
Really?
Okay.
ICC. Huh?
8, 9.
8 and 9 are C and C. C. Really? People. Number 1 in part B. Who's bigger? Let's say bigger or smaller. It says smaller. All right, smaller would be F minus or F? F. BA plus 2 or BA? BA plus 2. Plus 2 means you lost electrons, so plus 2 is smaller. O minus 2 or S minus 2? O minus 2. As you go down the group, they get bigger. So O minus 2 will be smaller. Very good. K plus 1 or Na minus 1? And I'm sorry, that's plus 1. Na plus 1 is smaller because as you go down the group, they get bigger. All right. So once we get to the table, I need my graphics. All right. So there. All right, the table's a little odd looking, but there's the first 2 rows of the table. Okay, the left column is the dot diagrams, and the right column are the ionic structures.
Wait, does N have, like, are the blue dots they count?
Yeah, the blue dots count. I just drew them differently because I knew you were going to ask questions.
Okay, Z.
All right, Zn, it says an ion, right? What does an ion mean? It's an atom with a charge, right? So you have to include the oxidation numbers. What's the oxidation number of Zn? Positive 2. So what does plus 2 mean? Take 2 away. So Zn would normally have 2 dots because there's 2 electrons, and plus 2 means that we take them away. So I erased the dots and wrote plus 2.
Can you explain that? Ion of nitrogen.
So again, an ion of nitrogen means what? I drew 5 electrons on N, right? Which you probably drew. All right, and an ion means what? It's got a charge. So what is N's charge? Look at its group and tell me its charge.
-3.
-3. So what does -3 mean?
8 gain.
That's what the 3 blue dots are. There's the 3 it gained, and I wrote -3 on.
So we need to draw the dots it gains?
Yes. Remember, when you gain, you draw. When you lose, you don't. So if you look at our ionic structures over here, all of the ones that we drew pluses on, did I draw the dots when they were pluses?
Yeah.
Did I draw dots on the pluses?
I mean, no.
No, I don't draw the dots when they're pluses. Did I draw the dots when they were minuses? Yes, so that's what you do when they're ions. So N being a -3, I did what? I drew the dots in. But on the +2, I did not.
But I thought that was just dot diagram.
Huh?
I thought that was just dot diagram.
It is, but we call it an ion, so it works the same way. I know you're hating this too. All right, how are we doing on checking the ionic structures? We need to pick up the pace of homework a tad here. We're never going to finish our notes today. Well, the test is Thursday. It's not moving, whether we get finished or not.
Why don't we do this?
So there possibly be things we're gonna do tomorrow.
Well, we won't have time to review tomorrow, which will be bad.
Fine.
Most of us probably need it.
Yes. Wait, how many dots are on the CL?
7, or there were 7, and then you put in an 8th one. So there's 7 on the first one, and then on the other side there's 8 when you add in one against. Are we good? All right, and there are the Lewis structures. And you don't need to know that. That was just there from when somebody asked me. That wasn't part of the question.
Why couldn't you have 3 lines and no dots on this?
Which one?
The first one.
All right. So if you have S with 3 dots,
With 3 lines.
3 lines, no dots, and this, like that, all right, you have 2, 4, 6, 8, 2, 4, 6, 8. Everybody has 8, right? 2, 4, 6, 8, 10, 12, 14, 16, and you have to have 18 electrons, and you only have 16. That's what won't work. Does that make sense?
Yeah.
Yeah.
On the virtual calculator, which is big for me.
Yes. All right. So to review, what's the top geometry with the SO2? It's bent because there's 2 O's and 1 lone pair. The PCl3 would be triangular pyramidal, which is 3 and 1. And the SO2 would be linear because it's 2 and no lone pairs, 2 and 0. And the H2S would be bent because it's 2 and 2. But yes, you will have to be able to do geometries. That's non-negotiable. All right, last for the backside. The top section was bond type. So in number 1, NaCl would be what type of bond? Ionic. Number 2, H2Te, non-polar covalent. CO2, polar covalent. Number 4, non-polar covalent. Those 2 chlorines you subtract them. That's that diatomic molecule. And remember, we don't write Cl. We write it as Cl2, so you got to remember to subtract those 2 Cls. All right, RBS. You can either say ionic or polar covalent. That one landed on 1.7, so I would take either answer. I would take either one. And HBr, polar covalent. All right, number F, or letter F. I've put the answers on the board. I drew the Lewis structures for you there. All right, and then I labeled them. pH3 is an exception. All right, that one is a 0 when you subtract, and so that's why it's non-polar. It's the same one that was on yesterday's homework. But the rest of them are all very straightforward in determining polar or non-polar. Questions?
Wait, so what's pH3 non-polar?
When you subtract the P and the H, you get 0.
So do you need to be prepared for that?
What did I tell you yesterday?
No, but what's happening?
Because it's on the worksheet. I didn't create yesterday's worksheet or this one. I stole them from somewhere.
Huh.
Yes. Which one are you yelling? It's non-polar?
pH3.
That's because it's zero when you subtract.
Oh, is that what y'all used to say?
Yeah. Wouldn't want anybody to listen to somebody else's question. Anybody else? Question on the homework. Fabulous. You need a periodic table. If you would prefer to have your electronegativity table, you may have it, or you may just have your orange table. Doesn't matter to me which one, but you need a periodic table.
Yeah.
Now, you're getting 25 minutes maximum. So look at the clock. The reason I'm timing you, you need to learn to work under some time constraints. You have 78 questions on this test. Okay? This is small scale compared to what you have to get done on Thursday's test. If you can't do this in 25 minutes, you cannot finish the test Thursday. There's no hope for you. I'm just being honest. There's no hope for some of y'all. Yeah, while she's still doing her thing. All right, each box is a separate question on the quiz. Okay? So if you get one box wrong, it doesn't mean the whole line is wrong. Because each box is a separate question. Yeah. Yeah.
Do we have to show our work, like, up in Word at the very beginning?
You mean like adding up the electrons?
Yes.
These are either right or wrong. How many of you are still working? about now, he's still working. I got a lot of slumped over bodies, so I got Salem and today. So you two tell me when you're done. Because y'all still have a few minutes, about 4, I think.
Okay, President Ford.
And then you don't need any tables, or, well, you might need periodic table. If you don't remember where some elements are towards the end, but it doesn't matter which kind of table. Where's the back? Yeah, didn't you do the back side?
What? That's not wrong.
I just want to see the look on my face.
Yeah, so that looks.
You said there's a back?
I hate that.
You had it flipped over on your desk.
No.
You didn't? I thought you were flipped over. All right, find your notes. Find your notes. Now, believe it or not, the last thing we have to do in the unit is probably one of those things you will see on the state test based on the release questions. Remember when we talked about the 3 types of covalent bonds? What were the 3 types of covalent bonds? I said covalent bonds. I can try to covalent bonds. Think. Listen to the type of question I asked. 3 types of covalent bonds. Single, double, and triple. Okay? Which one was the longest?
Single one.
Single was the longest.
yeah.
All right, who would be the strongest of the 3? All right, who would be the weakest? Okay, you will see some of that on the state test based on the release questions if they stick true to form. Now, the stuff we're going to work on for the latter part of class today is the properties of ionic, covalent, and metallic bonding. What things they have in common, what things they don't have in common, and how it affects melting point and boiling point. It is not very exciting material, to say the least. I'm just being honest. However, a lot of this stuff pops up in release questions. So my assumption is always that if they throw it out there, that odds are good it pops up on the exam. Okay? So we will cover it again as we do some review. However, like I said, it's dreary. We're going to start with metallic bonding. I'm going to, and I don't know how you want to do this in your notes, whether you want to make 3 columns, whether you want to do it like me and make space for metallic, ionic, and covalent, I don't care. I'm going to make 3 boards. So metallic, ionic, and covalent.
How much does it mean?
It's hard for me to say because I really don't know. All right, I'm going to stick with metallic. If you want to just do metallic and then flip to ionic next, try that. I'll try very hard. I will try very hard to finish all of metallic before I go to ionic. I cannot promise that I will have not forgotten something, however. I will try very hard. For your ink writing people, I will try very hard. Now, when we did a metallic bond, okay, we said that a metallic bond was a bond in which electrons are donated to a region in space. It's called the electron C model. Now, when I had you write that definition down, most of you probably thought, that don't make any sense. Certainly doesn't make a whole lot of sense to me either when I learned it back in high school. So, I'm a visual person. Always have been. So I draw ugly pictures. So here's a cross section of a melon. So I want you to envision a whole bunch of nuclei. And in every nuclei, we know that in an atom, nuclei are surrounded by what? What surrounds the nucleus of an atom? Electrons, right? So around every nucleus, there are electrons. So these electrons that surround these nuclei are different than the electrons in ionic and covalent bonding because these electrons are able to move.
Okay? These electrons can go wherever it is they wish to go. Okay? Now, that's unique from all the other types of bonding. All right, so the electrons in metals are not locked into position. Okay? They are freely moving or mobile. Okay? So the electrons in a metal are not locked into position. They are freely moving or mobile. That's the reason that we refer to them as the C model. You can think of them sort of as a sea of electrons. They're able to go wherever it is they wish to go. Now, that's different from ionic and covalent, because in an ionic and a covalent bond, can the electrons go wherever they want to go? No, they're locked into place. Okay? Their electrons cannot move. But in a metallic bond, the electrons can move. Everybody with me on that? Yes or no?
Yeah.
The electrons in a metallic bond are not locked into position. They can move. So this is going to create some unique properties for metals that ionic and covalent bonds do not have. Everybody with me on that?
Only metals.
Huh?
Metallic or only metals?
Metallic are only metals. Okay? So when I say a metallic bond, that is correct. That's for only metals. Okay? That's for only metals. Now, everybody caught up with me? Yes or no? Now, can anybody name a property of metals that you might remember from another science class? Huh? Luster's one we're going to write down, yeah. Any others? They are harder than other things, yes? Can't hear you. Okay, they're bendable. That's going to be malleable and ductile are the two we're going to talk about. Those are the words we're going to use, malleable and ductile. Anybody remember the difference between the two of them? All right, that's the one I was wanting right there. All right, so some of the properties that you guys just gave me. Oops, I don't want that. I want to do this. All right. All right, number one, they are good conductors. I'm going to explain why in just a second. Good conductors of electricity and heat. Now, I didn't go into that when we did the periodic table because I knew we were going to do it here with bonding. But all metals are good conductors of heat and electricity. Jada said they're lustrous. Anybody remember what lustrous means? That's the nice science word. What? Means shiny. Now, I think it was Caroline who said that they were bendable. All right, there's two science words we use for bendable. All right, one is malleable and one is ductile. I think I spelled it right. Sorry, my spelling gets worse with age.
So that means the same thing?
No, it doesn't. That's why I'm putting them up here. All right, malleable means it can be rolled into sheets. Okay, so think aluminum foil. Okay, that's the best example I can give you that everybody probably has in this room at their house. Okay, things that can be rolled out into sheets are malleable. All right. Ductile means it can be drawn into a wire. All right. Copper wiring is a nice example. Looking around the room, looking at diamonds, earrings, those are very nice examples of things that are ductile. Okay. If we didn't have, I don't know what metal that is, if they're nice gold earrings, then that would be an example of gold that's ductile. But if that metal was not ductile, could she have those lovely hoop earrings? No. Okay. But the fact that metals are ductile allows us to have lots of different shaped jewelry. Okay. Now, these are all typical metal properties that we use. Now, we can also talk about hardness, which somebody yelled out, which is great. All right. We also want to talk about boiling point, which is part of our lesson for today. Now, these are going to be higher for metals. Why are these going to be higher for metals than ionic or covalent? All right, so how are we going to know that these are going to be higher for metals than ionic or covalent? Anybody know? How does metallic bonds rate compared to ionic bonds and covalent bonds? Is it a stronger bond or a weaker bond? A stronger bond, okay? It is the strongest of all the bonds. Okay? So when we talk about how hard something is or what its boiling point, and we could even include melting point here, it's going to be higher than an ionic compound or a covalent compound because its bond is the strongest of everybody's. Okay? Now, does that make sense? Yeah? Now, the last thing I want to talk about is how conductivity works. Now you can check for it. I don't know if my conductivity tester still works, but I can pull it out and see, but my battery's probably dead. All right. The one I have has a battery, it has a lead, it has a light, and that's it. Now, all we would have to do is put a metal here. You can if you want. Now, up to you.
Miss Walt,
Yeah.
can you stop that in an electrical socket where it like punch key?
No, it blows circuit breaker. That would. These are all ground fault circuit or ground fault. GFCI ground fault circuit interrupters. So these have the test reset buttons on it, so it would just trip circuit breaker. The old ones that don't have that would blow circuit breaker in the circuit breaker box, but most likely it would also char and leave some black stuff around there. but it would shock the snot out of you also. Yeah, I'm not willing to do that.
I say too.
Yeah. No, not happening. One of my favorite stories from years ago is I had a guy who was in jail on gun charges years ago, and I'd already taught the electricity in it, and he came back not knowing anything. It's like a big red wrapper in the outlets. What happens when you stick big red wrappers in the outlets? Yes, because they're living shock the snot out of me. Didn't take long to quit putting stuff in my electrical outlets.
Like
So I've got wires that run here. It's a conductivity tester. It's got a battery. It's pretty weak. It should be a lot louder than what you can hear beeping over there. So one's a light, one's a buzzer. It should be able to come on if I do this right. So you've got two metal leads here, and you got a current running down one from the battery, running down there from the battery. I'm going to put it on the metal here, see if I can get it to come on, see what happens here. It's pretty weak. All right, there it goes. All right, so when I hold it on the metal, what carries the current from this wire to that wire to make this stupid thing beep as and be irritating? Okay, that's what everybody always tells me. It's the wrong answer there. What carries the current from this wire to that wire? All right.
Can you stop?
Yeah, I could. It's kind of irritating, isn't it?
It is.
All right, so what goes from here to over there? Yeah. The electrons are moving through the metal the whole time, and they carry the current. So without those moving electrons, you could not carry the current from one wire to the other. Okay? So the moving electrons carry the current. Now, this is huge in understanding why ionic bonds and covalent bonds do not carry electricity and will not conduct. Okay? So, in a minute, when I ask why ionic and covalent bonds do not conduct electricity, what's the answer? The electrons don't move. All right? Electrons move in a metallic bond. That's why you never stick metal objects inside of electrical outlets, because electrons move continually. If you stick a metal knife or a metal fork in an electrical outlet, you're going to get zapped. Okay? Now, if it has a plastic end, probably not going to hurt. Now, an ionic bond. How is an ionic bond different than a metallic bond? All right, an ionic bond, first of all, is between a metal and a non-metal. All right, we know that. We know that electrons are transferred between positive and negative ions. All right, that's why it's called an ionic bond. All right, I tried to point that out when we went over the homework, but the word ionic comes from the word ions. So, when we talk about an ionic bond, first of all, and I have to draw a really bad picture here, and I'm sort of sorry, but ionic bonds form solids, form solid crystals. Let me fix my grammar there. Form solid crystals. All right. And there are 7 crystal shapes. I am not going to make you learn any of the crystal shapes other than to tell you that all ionic compounds form one of 7 crystal shapes. All right. When we do solids, liquids, and gases after we do the gas laws, I'll pull up the picture of the 7 shapes and show you what the 7 shapes are. But there are only 7, okay? So every ionic compound that exists worldwide has to be one of 7 shapes. So to illustrate how ionic solids work, all right? And I cannot draw for anything, so I apologize now for my terrible drawing. Yes, you need to draw it. Or something similar. Now, this whole thing that I'm drawing is called a crystal
lattice. Okay?
That's a crystal.
Yeah, it's just an ugly one. Doesn't it look like one?
No. Does that have to have a
Like
certain
sneaks.
number of those? girls?
No, it does not have to have a certain number. Okay, and it's an orderly arrangement of crystals. Now, inside the crystal lattice is what we call the unit cell. All right? And the unit cell is the smallest crystal that shows the type of, yes, my dear,
How are you?
we're good. How are you?
I have some lip fracture yesterday.
Not a problem. Who you want me to give them to? I'll take care of it.
Thank you so
You're welcome.
much.
Javante, Jada, and Tanae. Do it now or I'll forget. All right, it's the smallest crystal that shows the, let's say the shape. Let's say shape instead of type. Say shape of the crystal. Okay, now I'm attempting to draw something that's sort of diamond shape. Okay, so if I drew and shaded in that one diamond, would you be able to tell that the rest of my ugly drawing is diamond shaped? Sort of. If I was decent at drawing.
I mean, yes.
Okay.
I can't imagine it though. I did not draw these.
It's okay. If you, what you drew, could you tell if you shaded in your one shape, could you make out the rest of your drawing was that same shape? Okay. Well, the idea is that your unit cell should be able to tell you the shape of all the other unit cells. Now, clearly my drawing is bad, but if I know, but if it was good, my one unit cell would tell me the shape of all the other crystals in my crystal lattice. Yes, I'm sure.
I can't see it.
I just can't draw. I admit that up front. I told you all that way back in the first week of the semester. I'm terrible at drawing.
I'm trying to see. I can envision it. It looks like a honeycomb.
Okay.
Yeah.
Just not.
It looks like
They're all the same shape.
They're not all
Exactly. Thank you, Sailor. Thank you. They're all supposed to be the same shape. Okay?
See you ready.
I'm gonna say y'all are brutal on my self-confidence up here. Good thing I'm not in middle school.
Oh,
I might be suicidal by the time I got done teaching first period.
what? They got.
Most people have low self-esteem in middle school. All right. Everybody got it? All right, so a crystal lattice has lattice energy. Okay, all crystal lattices have what's called lattice energy. This is the energy needed to break the bonds in the crystal. Okay? It's the energy needed to break the bonds in the crystal. Now,
The individual crystal or the whole?
usually the individual bonds. It's not going to be the whole crystal. Okay? It'd just be the individual bonds.
Crystal, not shape.
Yeah, the crystal, not the shape. Now, the higher the energy, the stronger the bond. Does that make sense? So if it's a stronger bond, it would have more energy. Remember, triple bonds only in covalent, so it would not be an ion. So you want me to get real numbers? You want me to make up numbers?
Whatever's gonna make more
Real.
sense.
I don't know these off the top of my head. I'm not a walking encyclopedia. I promise I'm not.
Miss Wall,
Yes, ma'am.
do you send Annette Taylor to the office signing out?
I will.
Thank you.
Here, why don't we hope for a better day tomorrow if I check homework and that. Remember the sheet I gave you yesterday that I said we're doing tomorrow? Here's the one that goes with it. It's a possibility. All right, there's 4 of them.
Oh my God.
So, what can you tell me about these numbers?
They're there.
They are big. All right, but what happens to these?
They're going down.
They're going down. So, which one would be the strongest?
The LIF.
All right, so LIF would be the strongest. And as I go down the group, what's happening? They're getting what? They're getting weaker. You don't have to know why, it's irrelevant. All right, all I want you to know is as the numbers get smaller, they get what? They get weaker. Now, this one, if you look at the numbers, this one would be the what out of all 4 of them? It would be the strongest of the 4 because it has the highest number. Okay? That's all I want you to get out of this.
But it's not at the top.
No, it's not. It doesn't matter. It just has the biggest number. That's all you got to know for our class. Okay? Why numbers change, that's an AP topic. I'm not talking about that today. Okay? All you need to know for the purposes of what we're doing is that lattice energy is based on size. The greater the lattice energy, the stronger the bond. Okay? Are you okay with that? So, the greater the lattice energy, the stronger the crystal, the stronger the bond. Does that make sense? So, out of these 4 crystals I wrote down, which of the 4 crystals would be the strongest? So, who would have the greatest lattice energy? Who would have the strongest bond? Are we okay with that connection? That's all I'm trying to make here. I can't fix the Merry Merry Christmas. At least they're not doing that jingling a song from last year. That one almost put me over the edge. I don't remember the name either, but they sang it last November while Ms. Rector was out with her husband's surgery, and they were in here every day, second period, singing that jingling a song.
Oh my God. It was.
I told her she couldn't sing that before I retired again.
I just like making up words. That
That was awful. I don't ever want to hear that song again. She knows how I feel about it, though, so I'm not talking behind her back. All right, so what properties do ionic compounds have? Properties of ionic compounds. How do they compare to metals? All right, do their electrons move? Okay, so the electrons do not move. So what's that going to do? If they don't move, what things can't they do? Okay, they cannot conduct electricity. All right, what else? They can't conduct electricity.
Lower boiling point, melting point.
All right, so they're a weaker bond. Than metallic. So they have a lower melting point and boiling point than metallic. I will tell you it is still high though. It's just not as high as metallic. All right. What else? What were some other properties we had? What else can you tell me?
Not as malleable.
All right. So if they're locked in a crystal, think about a crystal. Are they going to be bendable or be able to be drawn into a wire? No. So what would happen if I hit a crystal? It would shatter. All right. So ionic compounds are brittle. Okay. They're not malleable or ductile. Not malleable nor ductile. All right, they're not malleable nor ductile. They're brittle. All right, what else? Are they going to be shiny? No. All right, these are going to be dull.
So it's wood in it? Wood in it? Wood?
No, not really. Wood's not going to be ionic. These are things like salt. All right. Now, can you make them conduct? Let me ask you that.
I mean, wait, okay.
Oh, you want me to go back? Hang on.
Yeah.
Sorry. All right. Well, Diamond's still writing. Can we make these conduct? You think so? All right. How? Okay. What are the conditions?
You don't know.
Yes, you do.
A science lab?
Google.
I can't make salt.
Yes, you can.
Just look it up, man.
Just look it up, man.
Excessive heat.
That would melt it. The salt melts.
Yes, it does. Yes, it does.
And don't pour it in water when it's melted. It explodes. YouTube.
What?
Can we do this?
What did he just say?
Molten salt
He said
explodes.
when you melt it, don't put it in water. It'll explode.
All right.
Can we try?
Salt will melt, first of all, which is fine. We cannot because we don't have a temperature high enough to melt salt. Now, can we put salt in water? I was gonna say, if any of you people cooked before, if any of you put salt in water,
Yes.
I do regularly. I like the taste of things with some salt and water. All right. I know my doctor's appointment is Thursday, and I should probably not do those things, but the doctor will probably yell at me with my salt intake. So I have no idea. I've lost weight, so I'm hoping I'm going to be off her hit list. All right. Can we make ionic compounds conduct? The answer is yes. And you've actually already told me both ways.
How?
What are the two ways?
In a science lab.
For the love of God, no.
Look it up.
In the microwave, no. What are the two things you've just told me to do?
Put it in water.
Yes.
Heat it up.
Put it in water and dissolve it.
Oh, that's the same thing.
Okay? Why? All right. You make moving ions or electrons when you put it in water. The salt dissolves. Now the ions or electrons are all able to move throughout the water. All right. Number two. You said melt it.
Yeah.
Now again, you've made moving ions or electrons. Both of those allow the electrons that were locked into that crystal lattice to move. The idea behind something being able to conduct is you need moving electrons. So all you have to do are make the electrons move. Once you put them in water, what happens to the salt? Dissolves. All right, if you have a container and you add salt, you make sodium ions, you make chlorine ions. They're able to move around. Everybody in here has been to a swimming pool, have you not? What do they dump in by the boatload every day? Chlorine. That chlorine comes as a solid. What happens when the solid goes to the swimming pool? It dissolves. Those create moving ions in the swimming pool. If a lightning storm comes up, what has to happen? You guys have to do what? Get out. Because if lightning strikes the swimming pool, all those chlorine ions are moving. Electricity hits those ions. Those ions are running around those swimming pools carrying electrons, and they're carrying that electrical current to whatever is in that swimming pool.
Is it more so?
Yes. Much more so than regular water. Okay? So you have to get out. Okay? Regular water will carry a current also, but not to the extent a swimming pool will, because all of these things are moving ions that are rushing that electrical current to you. Okay? So when you put an ionic compound in it and dissolve it, now you have those moving electrons. Okay? If you melt it, you have moving electrons. So you can make an ionic compound conduct.
So is it dissolving?
Same thing. Either way, you can melt it or dissolve it. Now, I can't melt salt in here because I think its boiling point or melting point, melting point is somewhere around 850 degrees Celsius, and I don't have anything that'll get that hot. You cannot do it in a microwave.
So are those the same thing? Or they different?
I know. Say what now?
Are those the same thing? Or they different?
They're different. Two different ways.
We used the little thing we used to melt it.
The Bunsen burner? Yeah, the Bunsen burner won't get hot enough. Okay? All right. Now, covalent compounds. Covalent compounds, all right, do not form ions. Now, if they do not form ions in any way, shape, form, or fashion, what do you know about their properties? They can't do what? They can't conduct. Okay? They will not conduct electricity. And we cannot make them conduct electricity. Because they don't have ions. There's no way to make them have ions. Now, covalent compounds are the weirdest of the types of bonding we've talked about. These exist as solids, liquids, and gases. Now, I will tell you that they are primarily liquids and gases. There are some solids, but they're primarily liquids and gases. They are the weakest of the bonds. Okay, they're the weakest of the bonds.
So they're a single one?
They can have single, double, or triple because this is covalent. Okay, so they're going to have the lowest melting point and boiling points. Okay, they're going to have the lowest melting points and boiling points. Now, I'm going to give you a new vocabulary word. These are what we call volatile. They vaporize easily. Any of my girls ever put fingernail polish remover on your nails? How long does it take to dry?
Forever.
Fingernail polish remover?
Oh, remover.
Seconds.
Okay.
Taking off your nail polish.
Taking off your nail polish.
Oh, yeah, that stuff dries quick.
Yeah, that's volatile. If you have to rub alcohol on your skin, how long does it take to dry? That's volatile, okay? Things that dry almost instantly when you rub it on something, that's volatile. Now, water, does water dry that fast?
No.
That's not volatile, okay? But things that dry almost instantly are volatile. That's why I said things like nail polish remover, acetone is one that would stick out to me that's volatile. A lot of you probably use non-acetone removers, but I use acetone a lot in college and organic chemistry, and it is incredibly volatile. All right? Spray it on something and it dries almost instantly. We use it a lot to dry chemicals. All right, questions. Now, tomorrow when we finish this, all right, we're going to do some things with Bowling Point. All right, so when we're doing this with Bowling Point, who did we say today had the highest bowling point? Okay, so we're going to start with metallic. And then who had the next highest bowling point? And then who had the lowest bowling point? Now, the only thing I have not gotten to that we're going to have to do tomorrow are these van der Waals forces. Okay? We're going to have to do that tomorrow. Now, because of that, I have given you 2 of your review sheets for homework. One of them I gave you last night and told you to start with. So the only 2 I have for tomorrow in class are the 2 multiple choice sheets. Okay? Test will be Thursday. No exception. I do plan to move on to some new stuff tomorrow. I know you love that. Alex,
So, what's all?
make sure you watch the video.
What's all video this?
Yeah, where does it start?
The test starts at the beginning of the periodic table, where we start talking about Mendeleev.
That's where it starts.
Where it starts, Mendeleev. Now, I will tell you there is some overlap in the last unit with this unit, like being able to read the periodic table, stuff like that. You will see some of that, because those are previous skills that you should still have.
So does it like quantum theory?
Actually, using quantum theory and photoelectric, no, but like being able to read the periodic table, groups, periods. If I refer to, like, if I say the halogens, I still expect you to know where the halogens are.
So it doesn't include electron configurations?
No, I'm not gonna ask you to write a configuration or draw an orbital notation. But if I draw the orbital notation, I'm going to expect you to know what it is.
So like here, where does it start?
It starts at Mendeleev, but there will be some overlap because of skills you should still possess. And I will be here today if anyone wants to do makeup work. Tell me y'all need to finish it. Alex, did you have homework for today?
No.
Really?
You didn't do the whole thing?
Yes. Bond type. We don't like tell you atomic, so that's polar covalent, non-polar covalent, stuff like that. Tracking the electronegativities.
That's it.
On the side of the thing?
Oh.